Okay, in this video, we're going to do an optimization problem. This is an open-topped glass aquarium with a square base is designed to hold 13.5 cubic feet of water. What is the minimum exterior surface area of the aquarium? So we are trying to minimize surface area. Okay, so that will suggest our model needs to be a surface area function in one variable. And then we'll deal with our constraint in a minute. Okay, so we got to introduce variables. It's a square base, so I'm going to call those x. I'll call the height y. And so in general, my surface area would be the area of the base, which is x squared, plus, now there are four sides, all of equal area for xy. Okay, and so I can't use the notation s of x yet because I have a function of two variables, so there must be a constraint we can use. And if we read the problem, it looks like, well, the aquarium has to hold 13.5 cubic feet of water. That's a statement about volume. So my volume is x squared y in general, but it needs to be 13.5, which tells me that y is 13.5 divided by x squared. And that allows me, in my model, to replace that variable with the expression involving x. And so now I can shift to function notation. So I can say s of x is equal to x squared plus 4x 13.5 divided by x squared. I'm going to clean this up a little bit. X squared, so 4 times 13.5 is 54. And the x's divide, so I get 54 divided by x. We might note the domain here, because that could help us limit to where to find critical points when it comes to doing the calculus. Well, I mean, our x value has to be positive, right? We're not going to have a negative side of a square base. And other than that, I don't think there's any upper constraint, because in theory, you could make this aquarium like really have a really wide base, you know, and then a tiny height and still have the volume required. So I really think the only domain is that x is positive. Okay, now we do calculus. I'm going to rewrite my, just to kind of prep, I'm going to rewrite this as x squared plus 54 x to the negative 1. I take a derivative. Okay, and now to find critical points. So a critical point would be where this is undefined or is equal to 0. It's undefined at 0, but that's already eliminated from our domain. So we're going to just examine when it's equal to 0. I think I'll switch to this. Okay. So actually multiplying both sides by x squared, you get 0 equals 2x cubed minus 54, which means that 54 is equal to 2x cubed, or that x cubed is equal to 27, which implies x is equal to 3. Actually, I shouldn't circle right away. Okay, so there's a critical point. Now let's go, so we're sure the derivative is 0 there. Let's go examine that we have a max. So I'm just going to create a number line that starts at 0. And let's just make sure we have a max. So a critical point at x equals 3. Let's plug in a number such as, let's go back to our derivative here. If we plug into this version here, plug in a number like, how about, I don't know, 10. So if we plug in 10, you get 20 minus 54 over 10. 54 over 10 is 5-ish, so that's going to be positive, which means my function is increasing there. And for example, a number like 1 would be 2 minus 54 over 1, which is negative. So it's decreasing. So I indeed have a min. Great. So I answered the question. What was the question again? What's the minimum exterior surface area? I know that happens when the base is 3. So I'm going to evaluate the function at 3. S of 3 is 3 squared plus 54 divided by 3, which is 9 plus 18, or 27 square feet.